Welcome. Thank you for your time and thank you for joining this webinar, which will be mainly held by Thomas Schütz from PROTOS Software GmbH from Munich, Germany. He's an expert in architecture and also in testing. And as he's an expert in architecture, there's no surprise that the testing approach is also very structured and very much oriented towards test case code generation. And he will teach us a lot of things you have to consider by testing efficiently. Topic today is testing drivers and MCALs for embedded systems. So we will address the typical embedded community, but we will also have a look on automotive topics, as they are usually working with the AUTOSAR stack and the MCAL drivers. So I'm really happy to welcome Thomas Schütz here today. Thank you for joining us for this webinar and supporting us with your know-how, Thomas.
Thank you,
sorry, maybe one thing I would like to say is I've been working together with Thomas for many, many years. And as he is not only doing the webinars, he's also providing training for Eclipseina since many years. In fact, it was the first ever training we did. Was software architecture for embedded system. And this was in 2013, so it's 12 years already, Thomas. Thank you for sticking with us and teaching so many people out there. And now I will shut my mouth and hand over to you. Thank you for joining us.
Yeah, thanks, Annette, and thanks for the opportunity to be here again. And as Annette said before, we are going to dig a little bit into testing drivers and microcontroller abstraction layers, as it's called in AUTOSAR, for embedded systems. So basically, yeah, it's another word, but it's basically the same topic for a different market. So we can use the same technology for that. Now let's have a look at what we are doing today. So the first question is, why are we doing what we're doing? That's basically always the same question. Start with why. One of the biggest problems in embedded systems development, also in software development in general, is that the costs to fix a bug and to retest a bug are growing exponentially with time or with the state of your project. So if you detect a bug and retested it while, let's say, on unit test level, that's relatively easy to do, very fast. You get a fast response. It's cheap because you just push a button. It's all in software. But the later it gets in the process, for example, the integration test or a system test, that's much more expensive, much later in the process. And so the reaction time there is very, very slow usually. And after release, I don't have to elaborate on why that's not a good situation to need to retest something after release. So what we try to do with our approach, or what we're doing actually with our approach, is we bring the hardware-software integration test and the parts of the system test to the implementation. Please continue doing unit tests. That's very valuable, but it's only for the pure software units in your system. So that's not enough to test on unit level for embedded system. Now let's have a look at the different test levels and methods and how this relates to driver testing. So let's have a look at a typical embedded system. In this case, it's a hydraulic system, maybe a lubrication pump or something like that, or a hydraulic pump in a car or in a building. In this case, that's a lubrication pump. It's a real system with the motor, the pump, the hydraulic system, which is controlled by the electronic control unit with the power electronics, sensors, actuators, and so on. And inside this ECU, you have a microcontroller usually, with your software stack, with your application logic, and so on, and also with the drivers and the microcontroller abstraction layer. It's just another word for, let's say, the hardware abstraction layer in AUTOSAR systems or in automotive standard AUTOSAR. But let's use this as a synonym for drivers, for peripherals, for bus systems, and so on. Now, on which levels can we test? Let's start with the unit test, the pure software unit test. It's easy to do. Please do this. It's based on a software unit, which can be for example, a C module, a header and a source file, or also a class. If you're using C++, Java, or the like, it would be a class. That's a pure unit test. It's just testing one unit. Of course, you can also use a unit test tooling to do a software integration test, one level up. You integrate several software units into a little system under test, and then you can run a software integration test, usually also with a unit test tool. Here we see some units you cannot test really good. For example, a motor controller or something asynchronous concurrent. That's not so easy to test with a synchronous a sequential unit test. Because you need concurrency and so on. And what you also cannot test really good is the driver layer and the microcontroller abstraction layer in your microcontroller, because here you have pins hanging out and electrical signals going in and out. So you need somehow to stimulate those signals and monitor those signals to test those drivers. That's usually hard to do with a unit test. It's also asynchronous and so on, and you need hardware. So this would be the first step with a hardware in the loop test. So basically you need a smallest possible hardware in the loop test to test your drivers or your microcontroller based software on top of that. It's a hardware software integration test because we already integrate the software into the real microcontroller. So essentially, you take the pins of the microcontroller as a black box. So the microcontroller plus software as a black box. We look a little bit later how this relates to the driver testing. So one step up, we have a big hardware in the loop test. So for example, you integrate already some sensors, some actuators, power electronics. That's already really hard to do, and it's hard to automate, and is very expensive. You might need, for example, for a temperature sensor, you need a climate chamber. For power electronics, you need really much electronics around it to simulate actually a power electronics, or to simulate a motor or a battery or something like that. And in the end, you need a system test, which includes the real world system, in this case, a motor, a pump, and the real hydraulic system. And that's usually very hard to automate. Most system tests are not automated on that level. And and it's usually very late in the process because you need the complete system. So from top to bottom, you start with fast, often inexpensive tests, like a unit test. Then it gets a bit more expensive, but still you can run it very often with the hardware in the loop test, as a hardware software integration test. And then it got slower and slower and more expensive. So up to the big hardware in the loop test and the system test. You can automate a big hardware in the loop test, but usually it's harder to do because you need to automate also the hardware components somehow and the hardware errors. That's a big disadvantage, basically. But the advantage is you test a bigger part of your system. So there are always advantages and disadvantages in those different levels. So you should pick the right level for the right test to make it efficient. Let's have a look at the driver test and how it relates to your application test. We are only looking at the microcontroller now. That's sufficient to test the drivers. So the lowest level driver test would be a driver or an MCAL test. Then, of course, you also can run a basic software test for the services, for the protocols, and so on. And on top of that, you can run a hardware-software integration test on application level. That's again the smallest possible hardware-in-the-loop test. But we're focusing currently in this presentation on the basic software test and the MCAL test. No? Okay, so that's the focus. Now, the problem you have, you need to trigger the drivers for the test. So you do not get away, usually you do not get away with a pure software test, software unit test. Because, for example, if this is your driver, or here are your drivers and your microcontroller abstraction layer, for example, a PWM driver or a CAN or a LIN driver, analog, digital outputs, inputs, and so on. You need, you can stimulate them from software, but you need to monitor or stimulate them also from your hardware lines. So the signals here, that's hardware, that's electrical signals, usually 3.3 or 5 volt signals, and you need them to actually really test and stimulate and monitor your drivers. So how do we do that? Here on this side, we have the miniHIL system, our test system. On this side, the target microcontroller. And so that's your system under test, the drivers and the MCAL, or also the basic software, depending on what you want to test. Let's mainly focus on drivers at the moment. And now you need to, so in this case, the target microcontroller is not a black box because that's your system under test. So you need at least connect your test system or your test cases with your target microcontroller. And the target microcontroller software here, you need some kind of agent, stub software to actually drive the drivers, to initialize them, to set the values, to monitor the values, and so on. Because you do not have an application. You only want to test your basic software or your drivers. So how do we do that? On this case side, we have our test cases. We have the signal adapters that can monitor and stimulate those drivers here. We also have certain simulation protocols and so on. And in order to have a lot of generated parts here in the software, we generate from the protocol class, so from the interfaces to our target microcontroller, we generate a target agent protocol over a transport layer. We communicate with the target microcontroller. It's everything generated except for this transport protocol. That's something you need to implement technology specific on this side. On this side, it already exists. And then we generate the protocol that serializes the messages here. Then, of course, also the target agent gateway, the driver stub header, because there we need to call the drivers or get information from the drivers. And in the end, you only need to develop the stubs for the implementation of the actual calls to drivers. So, for example, in the driver stub header, you have a set PWM duty cycle that we know that we can generate this directly here from this interface description language. But of course, our generic system does not know that your current driver implementation, so you need to implement this and call the actual driver here. So that's basically the infrastructure we generate. And now you can, for example, run a test case by sending a PWM init to the target microcontroller. So the driver is initialized, and we can measure whether it's really zero. So there's no duty cycle, there's no frequency attached to the pin, so it's completely on low or on high, depending on the settings. And then we start the duty cycle again. The protocol is communicating with the target. The set duty cycle function is called, and here in the implementation you call your set duty cycle function in your MCAL or your driver. So, for example, those are already requirements for test cases that are required by the AUTOSAR standard, but they can basically you need the same tests for any other PWM driver. So every PWM has a duty cycle and a frequency. So basically, these tests are really similar. So you would set the duty cycle and the period, for example, and or the frequency. And now the PWM actually does something. It has a frequency, it has a duty cycle, and here we can measure it again. And in the test case, we compare it with what we actually did send before as a command, and compare whether the actual duty cycle is the required duty cycle. So that's the idea. Now, how do we do that? We have our miniHIL board. That's the blue one. That's the hardware. The idea is that we test a microcontroller at the pins of this microcontroller on signal level. So we connect the pins of this microcontroller. This would be the system under test over this patch panel here with wire jumpers with our test system. So we have many IOs on this system. It's very fast, so we can really run very fast test cases also. For example, for a motor simulation of cleaning equipment here from Kercher. For the motor, you need to simulate such a motor with 20-30 kilohertz. So that can be easily done with the miniHIL. If you want to test only drivers, you need to measure the things also with a certain speed. You want a certain reaction time, for example. You want to know that if you stop something, the motor, that within, let's say, 100 microseconds, the PWM is actually off. If that's a safety requirement, you need to prove that it's actually happening. So, and that's why we need hard real-time test cases. So on this side, we need certain things to make this happen. That's our test chip. We need the connection between the drivers and the test system. So we have components ready to use for the drivers, for PWM monitor or PWM stimulation, or for CAN, LIN, and so on. So for basically most of the signals you might have in such an environment. And on top of that, for a real application level test, you need usually environment simulations, open loop, closed loop simulations. We have software building blocks for this kind of simulation, or you can also develop your simulation on your own, or we can help you with that. And on top of this, we have the test cases. So those are the three things you need to run a hardware in the loop test. Signal connections, signal drivers, then the environment simulation, open or closed loop, and the test cases. And the test cases can also be asynchronous and concurrent. That makes it a little bit more difficult to run a hardware loop system in addition to the actual hardware you need. Of course, it's a bit more complex than a unit test. Okay, so that's the hardware setup. Now let's focus on the software here, because that's more work than setting up the hardware, is the actual software development, because you need the simulation, the drivers, and the test cases. We connect this miniHIL board then to a laptop or to your desktop environment, and here you have the modeling environment to describe the environment simulation, the interfaces, and the test cases. So that's what test on your desktop looks like. It's just a miniHIL next to your laptop, for example. And if you have MCAL tests, you might have many I/O variants and cables, because you might have, I don't know, 50, 60 pins that can handle a PWM, or could handle an analog signal or something like that. And you do not get away with such a simple setup here for a smaller or medium-sized embedded system test. That's okay. You might have more cables than that, but still okay. But for a real big basic layer, basic software test or MCAL test, it might look more like this. And if you have this kind of environment, we have a solution to switch between those different setups. So for example, at the same pin, you can have a PWM or an analog input or a digital input or output or a CAN bus and so on. And if you have a very generic basic software in a bigger system, you might want to test all of them in different combinations, and you do not get away with a simple wiring anymore. That's why we cleaned this up and have a switch matrix here for the MCAL testers here. So that's actually our own test system for our own MCAL tests for our miniHIL system. So a self-test of the miniHIL, if you want, with a redundant hardware against the redundant hardware. But that's also how the MCALs tests usually look for bigger chip systems like an Oryx or something like that. Now, one important thing, if you make continuous developing on your basic software, is to completely automate the tests. On one desktop, if you have many developers and maybe also in different locations and a bigger team and maybe one basic software team, but 10, 20 projects actually working with this basic software, you might want to completely automate the tests with continuous integration. So we have customers that have, let's say, 1 or 2 basic software teams, but 20, 30, 40 products with based on the same basic software. And in order to really automate those tests, including the applications, you might want to use continuous integration. So the idea is that every code change of every developer, doesn't matter whether it's in the basic software or in the application software, triggers to build, test, and potentially deliver the software also on the hardware in the loop setup here. So if, for example, you're developing the basic software, you make a change to the basic software, you commit it, the server here, for example, executes all the different projects, not only this basic software test, but also the application software test for all the projects that are using the current version of the basic software, for example, or also to check whether in the future it would be able to integrate this. But in order to run those tests, we first need to test the basic software, all the drivers. And here see, for example, different microcontrollers attached to the different miniHIL setups. So this would be an Oryx test, MCAL test. This would be a STM32 test, and so on and so on. And they're all completely automated. So there's no need to do anything manually. Every pull request, every commit, or whatever you do can be tested automatically. Yeah? So you test automatically for every code change of every developer for every project within minutes. And it doesn't matter where the actual developer sits, because if you have a team in Spain, in India, or wheresoever, then every commit still triggers the same continuous integration setup. Now, in some cases, or actually in many cases, you have safety critical systems. So for example, we have medical customers, we have automotive customers, avionics, and so on and so on. Many of those systems are safety critical. So for example, an airbag test in a motorbike or in a car, that's safety critical. So you might need to prove in your process, depending on the safety level and on the standard you're using and on the domain, you might need to prove that the test system does its job correctly. In order to help you doing that, we have a qualification support kit, which is let's say, an 80% solution for the tool qualification problem for many safety critical use cases. So we deliver templates for the documentation, and we deliver, let's say, 80% of the test cases you might need. Maybe it's 90, maybe it's 70% of the test cases you might need. So standards like PWM, analog digital inputs and outputs, certain bus systems, they can be standardized, those tests. But if you have a very special, I don't know, SPI test with a protocol on top of that, you do not get away with a standard test setup for, and we add those test cases, we or you add those test cases to the standardized qualification support kit. And then you can re-qualify the tool for your application or for your test setup. That's to speed up massively the qualification effort and to make the effort much lower for everybody. So you can speed it up by using our qualification kit, the templates, the tests, and the actual reporting, which is also standardized on our site. Now, let's have a look at our real-world demo. I'm using a little demo project. There are PWMs, there is a motor driver in there, and so on. So I can show you a little bit how this works. Let's switch to my development environment. Here we have the test system, and here is my test setup on my desktop. So that's the system under test. This would be a STM32 microcontroller. That's the test system. So the microcontroller where the actually test cases and environment simulation runs, and that's the wiring. So for example, here we have 3 PWMs wired. We have digital inputs for digital outputs on this side, digital input on this side to simulate the Hall sensors. For a motor simulation, we have UART protocols running over those 2 cables, and so on. And now we can develop test cases for them. So the first thing we have to do, we have to use those adapters. Most of them are standardized, like analog adapter, digital output adapter, UART, and so on. Also duty capture units for measuring PWMs and Hall generators, for generating Hall signals, simulation for motor controls, and so on. Those are typical standard elements we deliver. For example, here you have 4 analog outputs. They correspond exactly to those 4 pins here. I'm going to show you this. They correspond exactly to those 4 pins here. And so now I can either connect them directly to my test cases, or I can connect them to environment simulation. For example, if you want to, or a protocol, like in the UART case, that's not the real UART adapter, that's the real UART adapter. On top of that, I need to simulate the protocol that's communicating over UART. Maybe I don't want to test only the UART, but also the protocol on top of that. This would be a basic software test then. And so I can add more and more layers to my test case. For example, not only test whether the physical layer or the driver layer of my CAN works, but also whether the right signals for example, a CAN database or a specific LIN protocol, whether they actually work in my basic software. So depending on what you want to test, on the layer you want to test. Now, last but not least, you also need to define test cases. So on this level and on this level, we have mostly state machines. So for example, this motor simulation is a state machine. That's a real state machine that generates code. You can run very complex simulations there. You can also integrate Simulink models. If you have already predefined simulations, we can generate the code and integrate those models into our test system. You do not have to remodel them. And and now last but not least, that's for example a stimulation for a motor temperature sensor, which stimulates an analog output, which on the other side is an analog input, and we measure the temperature there. Now let's assume we want to test the let's say certain IOs. We could, for example, send a UART to the other over this UART protocol adapter, a command to the other side, to the system under test, to start a PWM, for example. We can measure this here with this duty capture unit and evaluate it in the test cases whether the PWM value I did set is actually the same one I measured now. So, and maybe within a certain time. So let's have a look at the test cases. I want to introduce you a little bit to the test case modeling here. That's also a model. It's a textual model. Actually, all models are textual. So for example, this model essentially is also a textual model with graphical editors and viewers. So I can work graphically, I can work textually. So I can also reuse those very good built libraries on textual level. I can make pull requests, commits, and so on. So it's all integrated very well in your normal development environments. We also have a Visual Studio Code integration here. And now the test cases. So for example, I designed some test steps. So I want to send, for example, I want to send a certain speed to my system under test, or set a PWM, for example, on the other side. And then I expect a certain reply. So that's the action, and that's the reaction. So here I can say, okay, what other commands do I have here? I have activate BLDC and so on. So those would all be basic software items. And now I set the speed, for example, and then I can check whether my simulation that monitors the IOs actually monitors the right speed. Yeah, and by that I can evaluate everything. Here on the right, you see all the test cases are generated also automatically as sequence diagrams. For us as human beings, and also for the documentation, we understand diagrams much better than this. That's actually very simple, but if you go one level up and model some test suites or test sequences, it gets more complex. So in this case, you see this test case consists of several steps, and the test suite even has a lot more things running inside, a lot of loops and so on. So that's just as a documentation on to discuss the test cases. And now I can generate everything. So environment simulation, the drivers and the test cases, and also on the system under test, the adapters for the stub software. And now I can run those, I can connect to my system under test, and I can run those tests directly from here. So that's, you can use the graphical user interface, but you can also use the command line interface, for example, for continuous integration. We have a command line interface because you want to integrate this seamlessly into any kind of continuous integration server. So now while the test is running, I'm pulling a cable here. So let's start the test. I'm connected. Now let's start the test, and I'm pulling a plug here. So it's running. So now I pull the plug. Putting it in again. So I fixed it. So I simulated a driver failure, for example. And here you can see the results. So almost everything is green, but here I have a failed test case. So I sent something over UART, and I did not get a response over UART. This might be a driver failure. So I click on the timeout here. So they sent done came back, but then it ran into a timeout. And in my development environment, it leads me exactly to the point where the driver failed, or whether the test case actually failed. So now I have to dig into my system under test and see why, for example, the UART did not send this message. So this would be as near as you get on the test side to the problem. And this should be relatively easy to fix in a low-level driver. And if you fixed it, you just rerun it. You can also rerun only one test here, and if everything's green, it's okay. So this would be the setup on your desktop. if you develop test cases, or for example, if you want to debug into a problem you've just found in your test cases. It's good to have the board on your desktop, because then you can set a breakpoint, for example, while the test case is running, and see why the driver did not work. That's a very convenient way to look for problems in your software. You can also do this on application level. But on application level, usually a breakpoint is not a very good idea, because then your application will fail epically, because if you have a motor running or a CAN protocol concurrent several threads, a breakpoint is usually not very good to find out what's happening in a concurrent system. But for that, we can use the generated sequence diagram to see what actually happened, at least on a test level. And that's very convenient to debug your test cases, also concurrent test cases. Okay, so now if I'm working in a bigger team, I might have continuous integration, and of course I have a continuous integration setup here. So let's have a look at the continuous integration setup. In this case, I have a locally installed on my laptop a Jenkins server. It can also, of course, run on a server. The only thing you need an agent or a slave or a runner locally that to connect the cables to the miniHIL and to your system under test. Of course, you need to connect those cables to your runner, but you can do the rest. You can do it completely in the cloud. Everything on command line. So let's change something in our system under test. Now that's the code for my system under test I'm calling now. For example, here let's take the motor control, for example. I'm looking for a duty cycle. So on a driver level, I'm modifying now the set duty function to emulate a problem. Let's put the duty cycle constantly to 20%, and let's find out whether the problem is detected. Now I have a continuous integration and a Git repository locally. So let's modify here something we do not need to change. So, and that's the change I did here now. This one line I changed in my system under test. And now if I commit this, let's call this bug. If I commit this problem, just a second. Yep. Now I commit this, and immediately the continuous integration server detects the commit and starts the build process and the test process. So now here you see the continuous integration server. I didn't push anything. Now here you see it actually detected the change in the Git repository. It's a Git repository also locally for demonstration purposes. So I don't need the network. But it immediately starts to check out the change. It assembles the project. So you can see how it builds the actual project. It's everything command line. Then it flashes the system under test. Here you see it stopped. Now it's blinking again. So it flashed the test system. Now it flashes the system under test. It stopped. Now it's blinking again. So it flashed both parts, because I could have changed the system under test, and I could have changed the test system. And now I see it failed. Yeah. So let's have a look at what happened here. Yeah. Okay. I already know what happened. Sorry, I made an error. I could look at the log. It was not able to actually run the test because I'm still connected over the same interface with my graphical user interface. Of course, it's only one interface, so I disconnect this and rerun the test. So my fault. But you see, it's no big deal. You just rerun if you make an error like this, you just rerun it. And usually at the continuous integration, you don't have the graphical user interface. So again, it's built, it's flashed, and it runs the tests. Again, flashed here, Now it runs the test. While the tests are running, you can have a look at them. So here you see the textual log of the test cases. Yeah, just the older version of the logging. Yeah, here the test cases are now running. So, and in the end, you can see the tests are the build process is yellow. So red is it did not build, it could not run the tests. There was a fatal error because I've connected the wrong interface here, and yellow means there's actually a problem with the test cases. So it did build, it executed all the test cases, but I have a problem with my test cases. And now let's have a look at the test cases. For example, the test motor control speed or test limit temperature, they produced an error. And if I want to exactly know what happened, so let's have a look at the detailed log, at the detailed trace of the integration tests here. And here you can see, here I have the failed expect. I click on the expect, and in the, and in my development environment, it shows me exactly which step did fail. So, and that's very important because you get a very fast reaction on every commit, on every pull request. And fail fast is one of the most important things in continuous integration. So if you get a message after 5 minutes, you still know what you changed. Yeah, you had a couple of lines you changed, and nobody else, or maybe only one or two other people committed the changes. So it's very isolated. You can fix the bug and rerun it even before anybody else runs into the problem. Maybe on your branch or on the pull request or whatever method you use there. Okay, so that was the demo. I hope you enjoyed my little demo, and if you have any questions, don't hesitate to contact me directly if you want. Yeah, thanks for your attention, and thanks to Annette. Back to you. Thanks for the opportunity to talk here.
Yeah, I guess, Thomas, you're not finished because we have questions again this time. So
yeah, sure.
I will just go through the questions. So the first one, you see it now also on the screen, is from Konrad Tucher. What cycle time can we achieve for individual test steps?
Yeah, since it's an event-driven system, we can, on the main processor, we can go down to, let's say, 10, 20 microseconds. So really microseconds. So for example, if you test a motor controller, we simulate this with 20, 30, 40 kilohertz. So this would be 20 microseconds, something like that. The fastest reaction is actually, let's say, 10 microseconds on the microcontroller we're using for the test system, and with this model-based approach. That's very fast for a hardware-in-the-loop system, for a generic hardware-in-the-loop system. We can get even faster by using FPGA. We have an FPGA adapter, which is rarely used because the basic system is already really fast, but we can plug this onto our miniHIL board, and yeah, then there we can go down to 50 megahertz, something like that. So if we simulate, for example, radar sensors, this would be a driver test and the evaluation of the software that evaluates the radar sensors for certain cars or bikes or something like that.
Okay, I hope that answered the question. The next one is, can we test also a software component from application layer? So I guess this is a question coming from automotive AUTOSAR framework.
Mm-hmm. Well, we do not have an AUTOSAR stack on our miniHIL. So if you really want to trigger something on component level in AUTOSAR, you might need to use another software that triggers that. But we can for example, run the complete motor simulation for a motor controller, or the simulation for a battery, or bus protocols. We have code generators for CAN, LIN bus, and so on, to simulate those bus protocols on a signal level. So you can combine this very good with certain with application level. If it's not AUTOSAR, then we can test complete applications. So we have many medical devices and also automotive devices. We test completely on application level for the complete ECU. So that's absolutely possible. Yeah. With AUTOSAR, we would need to discuss with you exactly which use cases to have. Send me an email, we make an appointment, and we can discuss your requirements and think about whether it could make sense to use the miniHIL or not. I will always be honest with you, because you need to be happy with the solution.
Thomas, maybe now I have questioned myself. Yeah, is it that with the software components, it's a topic of interfaces, meaning that you are currently not supporting the RXML files, which are specifying the interface of the software components?
Yeah. So on driver level, we can support this, but not on component level. So on application level of AUTOSAR, you would need to trigger those events or those components from another tool. So if you have a pure AUTOSAR component test, then the miniHIL would not be the right solution. But if it's a combination, it would be worth having a look at it and see whether the miniHIL could add value to your test setup or not. This cannot be answered in general, I guess. We would have to look at the use case.
Okay, thank you. And then there's another question. I think it's the same person. Can we also test RF high frequency applications?
So this depends on the frequency. As I said before, we would need to think about, first of all, which frequency are we talking about. So high frequency in different domains can mean very different things. So if you give me a frequency or concrete frequency, I can answer this question probably. But yeah, we would need to have a look at the exact use case. With the FPGA, we can do pretty much in that reach. But if you have let's say a high frequency audio or whatever, or a 10 gigabit interface or something like this, that's not what the miniHIL has been made for. But please send me an email with the details, and then I can get back to you, or we can make a brief call and discuss your test requirements there.
Then we have another question. Testing MCALs and HALs separately from the full application is key enabler for safety and robust integration. Great topic. So we're happy about this. The question is, what about logs? Do you save logs for every I/O during a test execution?
Yeah, we can. The problem is more a performance problem, and a frequency problem. It depends on the frequency you need and on the number of I/Os, of course. Yeah, we can log the values, the digital and analog values of the channels, and the faster you need them, that more problematic it gets with the speed. What we do sometimes is a combination of, so if you really need a high frequency log, then probably you should use, for the higher frequencies, maybe a logic analyzer. We use a SAREA, for example. I have something here. That's a really good solution for the high frequency things, and for the low frequency things, you can get away with a log of the miniHIL signal log or event log. So sequence diagrams you've seen, they are event based. So They do not need much performance, but the cyclic things like analog inputs and so on, or PWM also, they take much more frequency. And yeah, we can log them on a miniHIL directly, but if it's more of them, eventually you run into a performance problem. But that's similar for, I guess, for most systems.
We have another question. Can you please explain me how a miniHIL board sends signals to the system under test? In this case, STM32 Nucleo. Also, is there any load box integrated to simulate DTC? I think DTC means diagnostic trouble code, or does it mean something else?
Yeah. So if we're talking about diagnostic systems, so for example, we have implementation for LIN and CAN for diagnostic communication, depending on what exactly you need, because not everything is standardized. So the diagnosis protocols are base layer, and of course you need to implement your protocol on top of them. But we have already many customers that use those protocols. So yes, we can do this. Usually, if this means diagnosis. And here you see STM32 in this case. Basically, I hope I understood the question right here. What we do is the pins of this microcontroller, they are mirrored here on those pins, and we mirror them on those pins here. So that means, for example, the red cable is connected to one of those pins here. So that's a standardized adapter of ST microelectronics. So we can handle basically all the Nucleo and Discovery boards with the same setup here. We also have other adapters for if you're in the domain of automotive, for example, for TLE, for Oryx, and so on and so on. So basically what we do is we make passive adapter boards, passive evaluation boards for specific microcontrollers, 3.3 or 5 volt. So basically that's how we adapt the microcontrollers to our miniHIL. You can also use for a first setup to place the evaluation board you have next to the miniHIL and wire it directly without those adapters. In the long run, it's a good idea to have a mechanically and electrically more stable adapter here, especially when you're running continuous integration. You do not want to fail something because somebody tripped over the wire or something like that. That's not a good idea. But yeah, for a fast startup, you can use this this direct wiring with an evaluation board. And and STM32, why we use this? There are many applications out there, especially in fields like medical and so on, with the STM32, and they did a really great job in standardizing the evaluation boards. But of course, we also have, 30, 40, 50 other platforms we support. We might be able to give you a standardized solution from us. Sometimes we need to build something special for because you have other chips attached, like a system chip or something like that. In that case, yeah. But it's standard for us to provide those interfaces or those adapters. You can also develop them on your own if you want. Hope this answers the questions.
So Thomas, I got the feedback DTC is in fact meaning diagnostic trouble code. I'm not sure if you completely answered this question. The second, there were two. Yeah. Also, is there any load box integrated to simulate diagnostic trouble code?
Yeah, so that's a field I'm not an expert in. I would need to ask my colleagues about this. Of course, I do not know all the details about all the domains. We have virtually in every domain we have customers. So, but please send me an email again with this question, and I'll get back to you with a concrete answer, and I connect you to the experts on our side. Yeah, please do that.
Okay, thank you. Another question. can you stop test execution at some point with breakpoints and measure some I/O?
Yeah, that's actually something we implemented for our automotive customer. The use case is we wanted to introduce or to inject a failure in a driver for a I guess for a flash or for a EEPROM or something like that. So the test case was to create a white box test. So the EEPROM was attached to the system under test. They wrote something to the EEPROM and they read it, and then we set a breakpoint on the system under test. We modify for example, the checksum before it's evaluated, and then we restart the system, or we run the system after the stop, and see on our system, our test system, whether, for example, the right diagnostic message comes or the right CAN message with the error of the EEPROM, for example. This would be a white box test. We have a solution where we can attach the miniHIL over, for example, over USB here with the laptop. And on the laptop, we can, over Python, for example, we can control a debugger like an STM, ST-Link, I guess it's called, or J-Link debugger, and set breakpoints here. We have also the possibility to generate from A2L files to generate the calibration protocol or the XCP protocol for different transport layers also, where we could also, which we use also for white box testing to modify or read memory on the system under test. That would be a standard from the automotive field. So those are white box testing methods. We suggest to get away without white box testing, because essentially a hardware loop test should be a black box test and should be a validation on a higher level. But if you have certain aspects you need to test in white box for safety reasons, for example, then we have solutions for that. But it's a bit more effort than the standard setup. Yeah, but you can do this. So this was the short answer to this question. Yes, we can do that.
Yeah, thank you very much, Thomas. So we're now through with all the questions, and also for everybody who put a question and stayed until the end to have everything clarified. Thank you for joining us and staying until the end. And as Thomas said, you can contact him anytime to get more information or to get your topics clarified with PROTOS directly.
Okay. Yeah, thanks, Annette. And have a nice day to everybody.
Thank you. Bye-bye.